Okay, welcome to this first colloquium of 2022. This colloquium is dedicated to mathematical physics, and we will have the next colloquium again this month. There was some change of plans, which was largely my fault, actually. And therefore, the next colloquium will be on February the 16th, and will be dedicated to, if you want, aspects of turbulence, and if you want chaos from a physics perspective. Our guest will be Angelo Vulpiani from the University of Rome La Sapienza. So I will let Stefano introduce the speaker, Corinna, whom I would like to thank for accepting our invitation. Thank you very much.
So welcome everybody. I'm very happy to introduce Corinna Ulcigrai. Corinna is a professor at the University of Zurich, and before that she was a professor at the University of Bristol in the United Kingdom, and before that she was a PhD student in Princeton under Yakov Sinai, and before that she was actually a student at the Scuola Normale, which is when I first met her. And Corinna is a specialist of dynamical systems. For the non-mathematicians, dynamical systems are that part of mathematics which tries to understand how systems evolve in time. And in particular, she is an expert of ergodic theory, which is that part of dynamical systems which speaks a lot to statistical mechanics and other branches, because it talks about distribution of orbits and statistics of orbits in some sense. And she has been, as I mentioned, a PhD student of Yakov Sinai, and she has received several grants and prizes, most notably the prize of the European Mathematical Society in 2012. Which is a very important prize. If you look, the list of the graduates is very impressive. In 2012, there was another Italian graduate, Figalli. So it was a very good year for the Scuola Normale. And she was awarded the Whitehead Prize by the London Mathematical Society the year after, in 2013. And finally, in 2020, she has been awarded the Michael Breen Prize in Dynamical System, which is, in our field, at present, perhaps the highest recognition in the field. I think I've introduced Corinna, and she can speak for herself. She's a fantastic speaker, and you will enjoy her talk a lot. Okay.
No pressure. So no thanks pressure. A lot to Stefano for the introduction, and to all the organizers for the invitation. So it's of course a great pleasure for me to give a colloquium at the Scuola, of course, because I was a normalista myself, because I studied there. So, and of course it's my alma mater, so I'm very honored of coming back as a speaker. And again, I was told to prepare a talk not for mathematicians. So I already apologize to the several mathematicians in the audience. The talk is not targeted to you, even though maybe at the end I will try to say something hopefully of interest to everybody, but we'll start very slowly. And with the notion of chaos from the mathematical point of view. So I'm trying to explain what are chaotic dynamical systems. So dynamical systems are systems which evolve in time, and really there's plenty of examples. Almost everything around us is a dynamical system. The weather, you can see it as a dynamical system. The stock market, finance, you can see it as a dynamical system, or more classical models for mathematical physics like electrons in a metal or molecules in a gas. All these systems evolve, and they intuitively they are hard to predict. So we know it's hard to predict the weather accurately. It's hard to predict the stock market. And the reason for this is indeed their chaotic behavior. And we'll talk about what chaotic behavior means throughout this whole talk. And again, I'm not going to talk about the weather nor the stock market, even though I think Stefano Marmi has some work where he can also apply ergodic theory, and dynamical system can also be applied to finance but this is not the topic of my talk. The only example I will talk about today is mostly the third type. for example, with electrons in a metal and other dynamical systems motivated by mathematical physics. But before that, just a very common knowledge that you might have heard of, the notion of a butterfly effect. So all the systems that we are going to talk about today are fully deterministic. So deterministic means there is no probabilistic aspect, there is no noise, no randomness. They are completely described by clear rules that can be the law of physics and some system of mathematical equations. So there is no undeterminate behavior. But nevertheless, they do display chaotic features. They are hard to predict. And this is a phenomenon that maybe many of you might have heard about called deterministic chaos. So even deterministic systems can display unpredictability. And this is a very common public engagement. There are many books on doing popularization of mathematics talking about this. And you probably all have also heard about the butterfly effect. So this is one of the most important features of chaotic. There are various definitions of chaotic systems, but all of them include the butterfly effect. So the butterfly effect, it's an image which was used to popularize the work by Lorentz. And Lorentz was both a meteorologist and a mathematician. And he introduced this idea, mathematically it's called sensitive dependence on initial conditions. And in a system which has this sensitive dependence or butterfly effect, the idea is that a small change on the initial conditions of your system can create a very different long-term macroscopic behavior. And the image is that the butterfly, if you add a butterfly and this butterfly flaps the wings in a different way in Brazil, this little tiny change can create a huge effect. For example, can be the cause of a tornado on the other side of the world. This is a very common image of chaotic sensitive dependence. But what I want to focus today is slow chaos. And fast and slow intuitively refer to how quick, how fast this butterfly effect is. And again, so the idea is that you perturb a little bit your system, you change a bit your initial point, and this creates a divergence, a different evolution. And this divergence can happen quickly or slowly. And quick or slow is what characterizes fast chaotic versus slowly chaotic systems. And fast and slow means exponential or polynomial. So systems where if you change a bit the initial condition, the future trajectory diverge exponentially are fast chaotic. And slow chaos refers to the fact that, yes, if you change a little bit your initial point, you have a different evolution, but the divergence of these two histories is sub-exponential, could be polynomial or even logarithmic, so it's a slower growing function. And again, more officially in dynamical systems, we talk about hyperbolic systems as fast chaotic and parabolic dynamical systems as slowly chaotic, but I don't like these terms because they create confusion. Also, people working in PDE have a different meaning. And this is really, I like better the image or fast or slow butterfly effect. And again, fast chaotic dynamical systems are very well understood. I think the theory explaining their behavior started in the 70s with the work of Anusov and Sinai and important Russian school of mathematicians. But slowly chaotic dynamical systems are more of a zoo. So there are different examples that display different features. So we don't have a general theory. And the talk today is about what are the chaotic features, what are the properties of some slowly chaotic examples. And as I say, so yeah, dynamical systems sits a bit in between analysis and geometry. And it has connections or motivations from mathematical physics. So I don't like to think myself over as a mathematical physics. It has connection with probability, with number theory. So I know that there is a big debate in Italy about defining in mathematics what are the groups. And well, sometimes mathematics really spans across these boundaries. There are no boundaries. So dynamical systems is a good example of a mathematical field which has borrowed a lot from various subfields of mathematics, both in terms of techniques and in terms of motivation and applications. Okay, so that's something that I learned from Stefano when I was a student in Scuola Normale, and then made me fall in love with dynamics, and I haven't left dynamical systems since then. Okay, so digression apart, I want to start with a very simple example. When I give a talk for a broader audience, I really like to start with billiards, mathematical billiards, because they are a very easy dynamical system to understand. And something which is also related to my own work. So what is a mathematical billiard? So we all know what a billiard is, and maybe you played billiards yourself, and you know very well that how billiards in a pool move. So let's idealize the system. We have a table, which to start with will be a rectangle with the plane, and the ball with no mass, and there is no friction on this table. And you shoot your ball in a straight line in a certain direction, and it moves like a billiard ball with unit speed on a straight line, making elastic reflections at the boundary. So when it bounces on the boundary of the rectangle, the angle before and after is the same. And that's the picture of a trajectory. But it's differently than in the real game. We do not want to consider friction, so there is no friction, and we do not want to send the ball into the pocket. So we do not want our trajectory to end up in a corner. Those trajectories we disregard. We only study infinite trajectories, which, because there is no friction and they never enter a pocket, they will continue to bounce forever in our ideal billiard table. Billiard rectangles are not interesting mathematically. They are very simple to describe. But you can introduce new features simply by adding an obstacle, like this gray circle or gray rectangle is a scatterer, so trajectories bounce on it, or a barrier, or you can just change the shape altogether and look at billiards in polygonal tables, or in tables which have in general some curved boundary, convex or concave boundary. And we can also look in general, we'll see some examples soon of infinite planar tables. Okay, why? Why should we ever look at these systems? Clearly not to play better billiards in the pub or in the bar, but so first of all, there is a motivation from physics. So clearly the trajectory of a billiard ball moves in the same way than light or acoustic waves. So this elastic law of reflection is also the law of optics. So again, so there's a motivation of studying billiard trajectories from optics and acoustics. There are also simple mechanical systems. And if there is any student who did recently physics 1 at the university, you can try to write conservation of equations of conservation of energy and momentum for a system where you have two masses on a rod. An exercise, you can try to prove that the motion of these two balls bouncing elastically on a rod can be fully described by a billiard trajectory in a triangle. Actually, maybe if you took a course with Stefano Marmi, maybe he solved this exercise for you too. It becomes a billiard in a triangle, and the angles depend on the masses of the balls. And another famous example is so-called the Lorentz gas and related Sinai billiard that we are going to talk about later. So, and these are examples from the kinetic theory of gases and thermodynamics. So motivations come from physics. And personally, I really see that I think billiards are a very nice example, simple to describe example of dynamical systems, but hard to study. So they display a lot of variety of different chaotic features, and it's not always easy to study and describe the properties they have. And just to go back to slow chaos versus fast chaos, if we just take a square as a table and add an obstacle, if you put a circle or a rectangle, it makes a huge difference in the behavior, in the chaotic properties of the billiard. And by the way, both of these are famous billiards. The circle one, the circular scatterer is the Sinai billiard, and the rectangle one is known with Ehrenfest. Maybe I'll tell you later what they come from. So if you have a circular scatterer and shoot a beam of parallel billiard trajectories, so you basically have the same direction, but move a bit the initial point. Then after one bounce, because of the convexity of the scatterer, this beam of parallel trajectories will open up. There will be scattering or defocusing. So you see just intuitively that already with one hit, you have divergence of nearby trajectories. So we really see the butterfly effect. So trajectories which start close very soon diverge. And you can prove that this billiard is indeed a fast chaotic dynamical system. And this was indeed the seminal work of Sinai in the 70s. And Sinai won the Abel Prize for the highest prize in mathematics, together maybe with the Fields Medal. And one of the reasons, one of the quotes was that he proved hyperbolicity, so fast chaos of the Sinai billiard. The other example, when we have piecewise a polygonal obstacle, after one hit, parallel trajectories, you see, do not grow apart. They stay parallel. So there is no butterfly effect yet, but the only source of different behavior are the corners. So if some trajectory hit and another misses the corner, then you have divergence and future different evolution. So again, this is also a mechanism for sensitive dependence for butterfly effect, but it's much slower. And this is an example of a slowly chaotic dynamical system. Okay, so I hope this is it's an image of slow chaos versus fast chaos that I hope you can stay with you. So butterfly effect, we see it, and we see that sometimes it's faster or slower, and it depends on the features of the system. In this case, on the convexity of the scatterer. Okay, so we want to do dynamics. So we want to describe behavior of trajectories, ideally. So what type of behavior can we see? Let's use our billiard to describe possible behavior. The simplest possible behavior is periodic motion. So if you shoot your billiard trajectory in the right way, you can find an orbit which closes up. So after 4 bounces in this example, I will just retrace my steps and keep moving in periodic motion. Or at the opposite end, you can have a trajectory which is dense. So you can have a trajectory which gets arbitrarily close to any point in the billiard. Or you can have a trajectory, this is another example of a trajectory which is becoming dense. Or you can have trajectories which are trapped. They are neither periodic nor dense. And this is an example in the ellipse where you have a region which is filled densely, but the trajectory never goes in the middle. And again, even if the trajectory is dense, often we want to know more. We want to know if it's equidistributed. So I will not define this concept properly here. Intuitively, it means if it fills the space uniformly, so spending in each region the same expected amount of time. And just for contrast, this is an example in the square with the barrier of a trajectory which is not uniformly distributed. You see, there are some kind of scarring. So there are regions where the trajectory spends more time. In some corridor, they spend more time than others. Okay, these are elementary properties of trajectories, qualitative behavior of trajectories, but you can ask statistical properties. And one concept which is very important if you've never seen ergodic theory or dynamical systems is that chaos is actually good. So the more chaos, the better sometimes it is at the level of statistical prediction. And this is an idea which comes from Boltzmann, which comes, who was basically the father, the inspiring figure for the birth of ergodic theory. And Boltzmann had this idea that if the system is sufficiently chaotic, and the mathematical notion is ergodicity, if the system is ergodic, and this means for the mathematician, if you want, there are no non-trivial invariant sets. So any invariant sets has a system which preserves a measure, has the only invariant sets have measure 0 or measure 1, preserves a probability measure. Okay, if the system is ergodic, so sufficiently chaotic, actually, we may not be able to predict every single trajectory, but we can have a good statistical prediction of long-time behavior. So for example, we have Birkhoff ergodic theorem that tells us that when we have in the right setting with ergodicity, trajectories are uniformly distributed. Typical trajectories are uniformly distributed. Okay, so chaos is good. The more chaos, the better to have statistical description of most trajectories in the asymptotic time, asymptotically when time grows. Again, here is the definition of equidistributed that maybe I will skip. And you can go much beyond ergodicity. So we saw properties of trajectories like density, statistical properties of trajectories like equidistributions through ergodicity. And you can ask another important property I want to mention today in the talk is mixing. So we were with Augusto told you that next colloquium will be on fluid dynamics. Maybe they will talk about mixing in a fluid dynamic point of view, but mixing is an important concept, a mathematical concept. And again, let me show an example through a billiard. Mixing is not about one trajectory, but it's about the evolution of a set. So if I take a cloud of initial trajectories, a set A, and I flow it for a certain time, I evolve it for a certain time. So this is the picture of the billiard. So I have this cloud, blue cloud of initial points, and I see what they do when I move, when I let the billiard balls move. And you see they scatter, so they spread. So that when the system is mixing, an initial set of initial trajectories will spread uniformly in space. Again, this is another time the simulation. And the mathematical definition is also in terms of decorrelation. So if you have two observables and one of them you flow it with, you apply your dynamical system, then the two observables decorrelate. And we talk about decay of correlation in physics also. This is often used. Okay, so mixing, and there's more, it doesn't end here. So you have finite properties, weak mixing, mild mixing, multiple mixing, mixing of all orders. There are a lot of nuances of chaotic features that mathematicians have described and studied and differentiated. And you can go even beyond at the level of spectrum. There is an operator on observables, the Koopman operator, and the spectrum of this operator gives you even finer information on decay of correlation and chaotic features. Okay, so this was our basic introduction to dynamics and ergodic theory. And now I want to focus on some examples of slow chaos. Again, slow chaos are systems which are deterministic, but chaotic. So they have the butterfly effect, but it happens slowly, sub-exponentially. And I want to focus in the rest of the talk on two main examples, one coming from billiards that we already encountered, and one coming on surfaces and flows on surfaces. Precisely, I want to talk about the Ehrenfest model and the Novikov model and related to flows on surfaces. And again, what are the goals when you study these systems? The first goal is to understand which chaotic properties they enjoy. So what are the possible nuances? We saw there are so many properties, so can you describe exactly the features that the slowly chaotic system has? And the second is very important to me, it's to understand phenomena. So you understand the mechanisms which generate this chaotic behavior and try possibly to identify common mechanisms throughout a wide range of slowly chaotic systems. Okay, so let's move into the statistical mechanics world. And this is the very famous infinite billiard known as Lorentz gas. This is not the same Lorentz of the butterfly effect. This is another Lorentz who introduced at the beginning of the century this model. It's a model of electrons in a metal, so in the periodic setting. So you can think that you have atoms which are periodically spaced and electrons moving in the metal. And mathematically, it's simply an infinite billiard with periodically spaced scatterers, which are circular. And the trajectories of the electrons are billiard balls bouncing in between the white space. And yeah, so this is periodic billiard, and the periodic cell, which repeats periodically, is a Sinai billiard. So a square with the, here's Jakob Sinai, who, as Stefano reminded, was my PhD advisor in Princeton. And yeah, so the Sinai billiard is the cell of the periodic Lorentz gas. And another, to compare fast chaos versus slow chaos, another model in statistical mechanics is the so-called Ehrenfest model. So Ehrenfest are two, it's a couple, Paul and Tatiana, a few years after 1912 versus 1905. They suggested a modification to the Lorentz model. They suggested to use rectangular scatterers instead of circular scatterers in the Lorentz gas. This is again the periodic version, but periodically placed rectangles. And you play billiard outside in the white region. And again, they ask several questions about diffusion rate and existence of dense trajectories. And what is a bit amusing that when they introduced the Ehrenfest model, Paul and Tatiana, by the way, Paul was the physicist and Tatiana was the mathematician of the couple. They thought that using rectangles will simplify the picture and allow people to study this rigorously more easily. But it turns out that the history turned out to be different, because indeed the Lorentz gas, as we saw in our baby model with circles versus rectangle, you can believe that the Lorentz gas, because it has circles and curvature and scattering, it's actually fast chaotic. And the Ehrenfest model, because it has flat polygons as obstacles, it's a slowly chaotic. And indeed, it was easier somehow, not easy, but easier to, the results on the Lorentz gas came first, and they started in the 70s. I guess there is lots of people, lots of physicists and mathematical physicists, Spon, Galavotti, Boldrighini, Sinai, Buminovich, Chernov, Sass, Varju, Markov, Strombergson. I put just some of the key names. This was much studied, much understood. But for the Ehrenfest model, it's only 10 years. The last 10 years, it has been a bit of an explosion, but there was essentially no rigorous results from 1905 to 10 years ago. And breakthroughs involved the work of various people. I put also Arthur Avila, Fields medalist. And I've also worked on the Ehrenfest model, as I will tell you. And I'll try to tell you why it took so long.
Corinna?
So let me tell you what we know now of the Ehrenfest model.
Corinna?
And one result concerns the existence of dense trajectories. So in the Lorentz gas, you can prove that there are dense trajectories. And this is a simulation which shows a dense trajectory. This is a simulation which shows a non-dense, like fractal trajectories. And you can ask which of the two patterns is more common. So what I proved in joint work with Krzysztof Franczek, already several years, almost 10 years ago, is that actually the Ehrenfest model does not possess that dense trajectories. So for almost every direction, if you shoot your ball in a random angle, you will not explore all parts of space. You will see this fractal-like picture. And the stronger result is that the system fails to be ergodic And actually, the ergodic decomposition has uncountably many ergodic components. So it fails to be ergodic in a very drastic way. And on the other hand, you have other nice features. Trajectories are recurrent, so they come back. Typical trajectories come back. And there is an interesting physical phenomenon of superdiffusion. So in time t, the typical trajectory will travel up to distance t to the 2/3. This is more if there are probabilists, or if you've seen any probability in random walks. A random walk explore the space at the rate t to the 1/2 square root of t. And this is faster than a random walk. And okay, why did it take so long? And actually, to prove rigorously this 2/3 exponent is a beautiful history and success of the mathematical community, which is close to me, the community of Teichmueller dynamics, because this 2/3 has actually quite a deep mathematical explanation. And here to throw some harder work, it's harder words. It's a Lyapunov exponent of the Teichmueller geodesic flow on the modular space of abelian differentials. So, okay, there is some deep mathematics, and maybe at the end I will hint at, but it took very long because there is a lot of rich and deep mathematics needed to explain this, these results. And also in our work with Franczek, we use deeply these heavy mathematical techniques. Okay, so this was our excursion into billiards. And now I would like to move to the second type of system, slowly chaotic systems I want to talk about. And they are flows on surfaces. So here I have an image of a pretzel. Actually, I'm sorry, Stefano told me, now that the colloquium is not in person, I cannot be there and meet you all, which makes me very sad, but we cannot have an apéro, so maybe I hope it will not make us too hungry. You can go and get a snack if you are online. I don't see if you drink and eat when I talk. Okay, so pretzels. So this is a surface. So we are going to take a surface with G holes. Our pretzel has 3 holes, 3 handles. So some topologists in the audience will forgive me, but so, okay. So we take a compact close orientable surface, and on this surface of a donut, we look at a flow. So we look at the point moving on the surface. And a flow is just describing the trajectory of a flow is just the trajectory of my point moving. And you can think, if you're an analyst or whatever, you can think of solutions of a differential equation, for example, that describe the motion on the surface. So my surface, I really like that my surface is not a bagel, but it's a pretzel. I don't want bagels. I like pretzels. I like when there's more than 2 holes, more than 2 handles. The genus has to be at least 2. Because there's much richer phenomena, and indeed, bagels, tori, belong to the world of Hamiltonian dynamics, elliptic dynamical systems, and KAM theory, and many people who do work on these topics. But I like pretzels and genus too, because they give you slowly chaotic dynamical systems. And again, if you have a flow, so it has singular points, fixed points that can look as saddles or centers. And I'm going to look at area preserving flows. So there is some notion of area on your surface, which is preserved when you move a set along the dynamics. And again, more formally, we're going to talk about equivalently area preserved smooth, and area preserving means locally Hamiltonian. So locally on the surface, there's a Hamiltonian, and this, the motion is described by local solution to Hamilton equations. But geometrically, just think of motion on the surface, and area of a set is preserved. Or if you want to think of fluids, it's like talking of incompressible fluids. Incompressible is like area preserving. And incompressibility is the key assumption in ergodic theory. You want to study incompressible flows. Okay, motivation, again, there's motivations from physics, mathematical physics. So flows on surfaces appear for example, from the study of motion of celestial bodies in celestial mechanics. And this is really the birth of ergodic systems and ergodic theory and dynamical systems as a research field. It was motivated by the work of Poincaré at the end of 1800. And Poincaré was interested in the motion of planets. And actually the name orbit, or which is often used instead than trajectory, comes from celestial mechanics. And this is a classical example. The example that my work is closest to comes from electrons in metals. And again, there is a model in solid state physics due to Novikov model from the 1990s, which describes the motion of an electron in a metal under a magnetic field. And there is a semi-quantum, so semi-classical limit. And you can really reduce this system to a motion, a locally Hamiltonian flow on a surface, so a motion of a point on a surface of with some genus, with some number of handles. And this surface is the Fermi energy level surface. Good to mention Fermi in colloquium or scuola normale. And okay, so again, so we have a flow on a surface which is smooth and area preserving. And we may want to classify, describe what are the chaotic features that it enjoys. And ergodicity in this case, it's a key result which can be dated back to the 80s. Typically, in some sense, you have ergodicity. And this slide is a bit more technical, but I'll try to go over it quickly. Actually, mixing, we talked about mixing. Mixing is really some recurrent research team to which I started when I was a PhD student, and I went back and back. Actually, the full classification of when these flows are mixing or fail to be mixing is quite subtle in higher genus, and it depends on the type of singularities. If there are centers or saddles, simple saddles, multiple saddles. So the classification is quite delicate, and it started with my PhD thesis. So you have mixing in certain cases, and when you have mixing, you can actually describe the speed of mixing, how fast is mixing, and you get sub-exponential mixing. So this was a work of former PhD student of mine, Davide Ravotti. And so these are really, this shows really that these examples are slowly chaotic. And finally, recently we started going beyond, we said ergodicity, then there's mixing. And if you want to go beyond, you can study spectral properties. I don't want to go into this, but there is some further recent research on trying to understand finer properties about the spectral features. Okay, so now we understand a lot of the description of which nuances of chaos this important class of slowly chaotic systems enjoy. But I want to move into the third, there's the last part. So the next part of my talk is about the mechanisms. So I told you at the beginning, we want to understand slow chaos. We have important fundamental classes of slowly chaotic systems which appear in physics. We want to understand which properties they have. We saw the example of the Ehrenfest model and the Novikov model of flows on surfaces. But we also want to understand the mechanisms. What happens, how these chaotic features are why are they taking place, and how the system becomes chaotic. So I want to give you two examples of mechanisms for slow chaos. And one really important one in my view is shear. And this is a very particular way in which the butterfly effect happens in slowly chaotic systems. And the idea is the following: in many, I won't say every, but in a lot of slowly chaotic systems, you see this phenomenon. You start with 2 points which are nearby, blue and red, and you flow them, and the trajectories stay parallel. So the trajectories do not diverge. They travel parallel to each other. but one is faster than the other. So, and then sometimes I say, okay, imagine that you're on a highway and your two cars are traveling on the same highway, but from one window to another, you take an elastic band. Don't do this in a highway. And if one car goes faster, the elastic band between the two cars will shear, will bend, and at some point it will break if it's an elastic band. So arcs that transversal to the direction of motion shear, and the more they shear, the more they approximate a trajectory. The more they shear in the trajectory, in the direction of the flow in my picture. And this really happens, this shear happens in locally Hamiltonian flows, in our surface flows, when you have a saddle, a Hamiltonian saddle. So let me show you shearing. If you take a set which is transverse to the direction of the trajectories, what happens is that near the saddle, near this point, it takes a long time to points which come very close to get out. It's a feature of Hamiltonian systems. And so the points which go very close to the saddle slow down a lot, and the points which are a bit farther pass much faster through. So what you see is shear. So the points to the left are trapped, slow down. The points to the right go fast. And like in our highway elastic band picture, there's shearing. Okay, and here's a mechanism which I really think is fundamental in slow chaos. And I've had several of my works have explored this mechanism in completely different settings. And the idea is that if you have ergodicity, so let's remember, ergodicity means that the typical trajectory is equidistributed. So it's dense and uniformly distributed. And mixing means that if I take a set of initial conditions and I flow it, I move it, it will equidistribute. So one is about a trajectory, the other is about a set. And here's a recipe for mixing when you have, if you have ergodicity and the shearing, these two ingredients give you mixing. So it's a bit more technical. It's ergodicity needs to be unique ergodicity, and shearing is to be in the flow direction. But together, this is really important phenomenon. So I give you a hint of how this happens. So you have a set. And first of all, you cover it with arcs transverse to the flow. So this is Fubini for mathematicians. Each of these arcs that cover your set individually, when you flow it, it will shear if you have shearing. And it will become a long arc which approximates a trajectory. But the trajectory, typical trajectory, is equidistributed. So each arc via shearing will become equidistributed, and altogether the union of the arcs will also equidistribute. So this is how ergodicity plus shearing gives you mixing. So this is the only maybe a mathematical idea that I can give you. Of course, when you have to prove shearing, prove equidistribution, it's very technical. There are heavy tools and there is a lot of machinery sometimes that enters, but this is a nice geometric picture for slow chaos. And again, this mixing via shearing was used already in the end of the 70s by Marcus to study the horocycle flow. So if you know what the horocycle flow on a surface of constant negative curvature is, this is another very important example of slowly chaotic flow. And also in the context of nil flows, flows on the Heisenberg group, quotients of the Heisenberg group. I worked with Avila and Forni, and Avila, Forni, and Ravotti. It's not a preprint anymore. This is old. Okay. Okay, so it's ubiquitous. It's really, you can find this mechanism many times. And can you go beyond mixing? Is a shearing? Shearing is really important. I want to give you another second important tool for slow chaos. And this goes back to the work of Marina Ratner. So Marina Ratner, I don't even know if many mathematicians, unfortunately, have heard of her, but she was an amazing figure in mathematics, maybe not as recognized as she should have been. And so she was also a mathematical sister of mine, being a much older sister, but she was also a student of Sinai. And she died a few years ago. And her work, Ratner theorems, are some of the most important results that she has proven, are very important in mathematics in an area called rigidity, about classification of invariant measures for group actions, and homogeneous dynamics. So I will not enter into details, but she proved some important theorems which have also a lot of applications to number theory, to Oppenheim conjectures, and to billiards, but also to networks and a lot of physical and practical applications. And she, in her work, she used as a key tool a form of shearing that we call nowadays the Ratner property. So this is a quantitative version of this shearing phenomenon I was talking about. So you want to see this parallel trajectories and transverse arcs shearing picture with some quantitative properties that I do not want to describe. And because this shearing Ratner property was so important in her work, this led several mathematicians to wonder whether we can prove this Ratner form of shearing also in other classes of dynamical systems, in particular, for example, flows on surfaces which are locally Hamiltonian. And this has an issue, unfortunately. The issue are singularities. So let's go back to our 2 points that travel parallel to each other at different speed. If there is a saddle point in your flow, this saddle introduces a singularity. So it actually splits the future evolution of 2 trajectories. It creates even more butterfly effect if you want. But if you want to exploit this slow form of shearing as a mechanism for chaotic features, then when you have this splitting, it's actually bad because it's too fast and you lose control of nearby trajectories. So nevertheless, a few years ago with Joanna Kuaga and Adam Kanigowski, we could prove that the typical trajectories of a flow, on a locally Hamiltonian flow, of a smooth area preserving flow on a surface, when there are traps, okay, actually do have this Ratner property, not the original Ratner property, but a variation, the switchable Ratner property later introduced. So you can deal with singularities, and you can still use all the powerful techniques that Marina Ratner introduced. And with this, you can get finer properties. For example, for example, multimode mixing. So it's a more sophisticated form of mixing. I'm afraid my phone is ringing, which is very bad. So I have to, I'm sorry, I have to close it because if you, do you hear it? I'm afraid so. I think I need to close it. 1 second. Very sorry for that. Apologies. Maybe you had time to read the definition of multimode mixing. I have to head towards the end. So I want to say one more, maybe technical slide and a few words about the picture behind. Okay, so with this Ratner property, you can get a lot of fine understanding, and we are currently also still working on problems related to disjointness and Sarnak conjecture, maybe orthogonality. There are lots of applications of shearing and Ratner property. And lately we have been also getting the very first results on this spectrum of the associated operators. So maybe this slide I will say very little. But shearing plays also an important role sometimes in the understanding of finer spectral properties. And we also used it together with Giovanni Forni several years ago to solve a conjecture by Katok and Touvenot, two mathematicians, about horocycle flows. And recently it's been used to study flows on bagels in genus 1 with a stopping point and proved that they have countable Lebesgue spectrum. And in genus 2, I like higher genus, I like 2 pretzels, and we proved complementary that typically we can see purely singular spectra. So there is, okay, don't worry about this. There is a lot of research going on trying to understand what are the spectra of the operators associated to these flows on surfaces of higher genus. Okay, so a few words to conclude. I spoke about results, but apart from some heuristic idea, I didn't tell you much about the techniques and the tools, and I will not, but I want to leave you with one beautiful idea. So the word behind, so what do we really use to prove all of these results? Not all, but many of these results use a very important set of techniques known as renormalization in dynamics. And I know physicists also use renormalization. Well, Sinai was my, one was working in across physics, probability, and ergodic theory, and he also had this idea of renormalization group, renormalization techniques from physics, but the renormalization I'm thinking of is very dynamical and very geometric. It's not the same, but it's a powerful and very beautiful mathematical idea. And this is the idea that okay, you want to study a specific flow on a surface, and instead than looking at one flow, you look at the space of all flows. So you look at, you think of this mathematical system as one point in a space of all such systems. So you kind of change parameters, you change the surface, the Hamiltonian, and you think of a space, and you start deforming your system through some family of deformations. And this deformation in the space of systems is important because it acts as a zooming machine on your interesting original system. So your deformation has the property that it zooms, for example, rescales time so that you can see different scales of your behavior. You can study your trajectory at different scales. And if, for example, this renormalization is recurrent, sometimes you get some self-similarity or approximate self-similarity in your orbits. And these techniques fall under the name of renormalization. In dynamics, there are various types of renormalization. And the ones that they use here is renormalization on the moduli space of surfaces, and it's called Teichmueller dynamics. Okay, why would you do something so complicated? So if you're not a mathematician, you'll say, oh, mathematicians always introduce complicated abstract objects, but actually understanding renormalization is powerful, and it helps because often, or at least in these examples, renormalization is also chaotic, but it's a fast chaotic dynamical system. It's hyperbolic. And we understand fast chaotic systems much better. We have very strong properties, and we can exploit this interplay between zooming and understanding the dynamical features of renormalization to gain very precise information on the trajectories of the slowly chaotic system. Okay, this is just a picture, mental image, but it's really what is going on. And the techniques really come from this word of, and again, I think there's a lot of geometry, dynamics and geometry. There is geometry of the moduli space of surfaces and flat metrics with conical singularities. So there is a lot of interplay between dynamics and geometry. Okay, to summarize, I have a summary slide and the reference slide coming. So to summarize, I hope now you know what are slowly chaotic systems. They are systems which display the butterfly effect, but with slow speed of divergence. Important examples that come from physics include the Ehrenfest model of, again, comes from electrons in a metal, but the scatterers, the atoms are rectangles, or the Novikov model, where you have a Fermi energy level surface, which comes from metal, and you study motion on the surface. And the research directions in the world of parabolic dynamics include understanding the fine chaotic properties, which nuances of chaos these systems enjoy, mixing, ergodicity, various types of mixing, spectral properties. And at the same time, identify some key mechanisms which create these chaotic features. For example, we saw mixing via shearing or Ratner property. And again, there's a third trend. Sometimes there's hope to have some kind of order into chaos, not order into chaos, but among various parabolic behaviors, sometimes one can recognize some universal features. And another trend is to study perturbations and study to understand properties which are typical for perturbations. Okay. So I want to stop, but I also want to leave you, if you're interested in reading a bit more, if I made you curious about any of this topic. So actually I can give you references in Italian, which I normally don't do. So I wrote a few years ago for UMI, for Unione Matematica Italiana, for the rivista for the Matematica e la Cultura Società, a piece on mathematical billiards. Biliardi matematici, caos e ciambelle infinite, perché i matematici giocano a biliardo dai poligoni al modello di Ehrenfest. And I was invited at also at the UMI Congress in Pavia a few years ago. And I gave a talk on slow chaos in surface flows, specifically more on surfaces and these properties. So this also I also wrote a survey based on that, which you can find on arXiv also, slow chaos in surface flow, that's in English. And if you are a mathematician and you really want to learn more, I gave a course at IHS, Institut des Hautes Études Scientifiques in Paris. It's 8 hours, but they were all recorded in the YouTube channel and really explaining the results and the proofs, again, focusing on surface flows. So, okay, so with this, I'm happy to stop and answer any question you might have. And I thank you once more for the invitation and for the attention.
Thank you very much for this beautiful talk. So I will leave the word to my colleagues. I just have a curiosity, if you allow me.
Absolutely.
You described the Ehrenfest model and
yes.
you stressed the fact that it's not ergodic.
Yes.
Does it have some conservation laws that people have identified? Typically in physics, when you have this lack of ergodicity, you think of some quantity which is conserved.
Yes, but so first of all, I kind of lied, because when I said it's not ergodic, it's subtle. So first of all, yes, there is an obvious integral of motion, which all billiards in polygons have, as long as the angles are multiples of pi. So for example, if I go back to, so for example, angle can only take finitely many directions, actually 4 in the case of the Ehrenfest model. Maybe I can even just go at the very beginning when I have a simple. So there is an obvious integral of motion, and this is what is it? Yeah, here. So you see a trajectory here takes only 4 possible values. So you can travel upward in one direction, backward in the same direction, or in other 2 orthogonal directions. So this is a trivial. So when we say that it's so nevertheless, you have to already restrict yourself. So it's a 3-dimensional phase space, but you have one integral of motion. So you are on a 2-dimensional phase space, but typical billiards for example, when it's not infinite like the Ehrenfest, but when you just have a polygon with this finite integral motion, typically you do have ergodicity. So this trivial integral motion doesn't matter, but then yeah, so then you really fail to be ergodic in a bad way. So there's no obvious, because of these uncountably many ergodic components, essentially it tells you it's not so. But nevertheless, unfortunately, this is a good question, because in our work, it's quite technical. We use quite sophisticated techniques from infinite ergodic theory and essential values, and we do not have a clear geometric understanding of what are these uncountably many ergodic components. So I do have a dream at some point to go back to this non-ergodicity result and understand it more geometrically. And the only thing, the feeling that I have that actually it's not in the system itself, but there is kind of a cover. So there is you can add dimensions. Maybe the physicist, I should say, I should add the dimension in space. And maybe there is a higher dimensional word of which this Ehrenfest model is folding. So you have this, if you add dimension upstairs, there are probably some simple invariant quantities. There are kind of some planes, hyperplanes, which are invariant, but then they are crushed and collapsed into this Ehrenfest two-dimensional world. And so this mess that you see is actually the trace of some more clear non-ergodicity upstairs. Does it make any sense? What I'm saying?
Yeah, yes, thank you.
Yeah, so,
there is a question in the chat, and I would like
yeah.
to ask Leonardo Masci to ask it directly. Otherwise, I can read it. But
I can read it too. I see it now.
Okay.
So if you want to ask, yes.
I can. Yeah, sure. Yeah. Is there a relationship between the growth of periodic orbits and these slow entropies, like in the case of topological entropy?
Okay, so first of all, this gives me the opportunity to say something very important. So you mentioned entropy. So some people have different definitions of chaos, and some people say that chaotic means positive entropy and or positive diaphragm of exponents. So if you use this definition of chaos, all of my systems, slowly chaotic systems, are not chaotic. So the entropy topological or metric, it's 0. So all of the systems which I was talking about today, the Ehrenfest model, locally homogeneous flows, have 0 topological entropy. So, and as you say correctly, when you have a positive entropy, you expect exponential growth of periodic orbits. So the problem is that here you don't have entropy, but nevertheless, there are people, and actually Katok, who was one of the leading figures in dynamics, who try to introduce notions of slow entropy. So you can change the definition of entropy and study a slow form of entropy targeted to see this sub-exponential butterfly effect. And then you can prove results about positive slow entropy. And some people, especially Adam Kanigowski, has computed a slow entropy of a lot of the systems. And then you can use this slow entropy as an invariant, which allows you to distinguish between different types of parabolic behavior. And I don't know if, this you could conjecture that maybe this slow entropy may have a relation with periodic orbits, and the growth would be sub-exponential, though, would be polynomial, but I don't know any results in this direction. On the other hand, actually a very important question on billiards in polygons with rational angles is indeed the growth of periodic orbits. So if you you can fix the length, say the length is at most a million meters, I don't know, and how many trajectories of length at most a million that close up do I have in such a billiard? And this question actually, I don't know if Alice Eskin and won the breakthrough prize for dynamical system with €2 million, and for his work with Maria Mirzakhani, Fields medalist, unfortunately passed away very young, and their work on this modular space on surfaces and Teichmueller dynamics has applications on exact counting of growth of periodic orbits in rational billiards. And nevertheless, even there, it's a very hard question. And even the result is only, the growth is quadratic, but the asymptotic, the constant in front of this quadratic growth, it's very hard to understand, and they don't have a full result. So it's a difficult question sometimes to count periodic orbits growth in this slowly chaotic system. That was all what I wanted to say, but yeah.
Thank you very much.
Yeah, I see a raised hand.
Yes, there's another question.
Yes, can you hear me?
Yes, I can.
So first of all, I wanted to thank you for your explanation of shearing plus ergodicity mixing. I found it very nice. And I wanted to ask if sort of the converse is true. So
Yeah.
If we negate the shearing, can we say something about mixing, or more generally? Or more generally, are there sort of physically interesting conditions which you can sort of easily check, which negate ergodicity or mixing?
This is an excellent question, because indeed this is much related to my work. But so, okay, so the answer of your question, essentially it's yes, for certain slowly chaotic systems. So that this mixing via shearing, it's really a mechanism for mixing in slowly chaotic systems. So if you go to fast chaotic systems, where we have a hyperbolic dynamical system, this is really not true. So mixing usually happens in fast chaotic systems without need for shearing. And actually it's not due to shearing that mixing happens. I was trying to find a classification of properties of flows on surfaces. Maybe I'll try it here. So mixing via shearing is not a mechanism for mixing in hyperbolic fast chaotic systems. And there you have a different mechanism. It's not about each piece shearing and equidistributed. It's more about different pieces together going in random locations. They stay, maybe they break into smaller pieces, but it's a different mechanism. So no in general, but within slowly chaotic systems, the answer is almost yes. No, I cannot find I'll try to go back to, maybe not. Yeah, here maybe, okay. So again, I worked, for example, a lot on classifying mixing in this locally Hamiltonian flows, smooth area preserving flows. I didn't put the negative results, but so as I said very briefly, whether there is mixing or not depends on the type of singularities or whether there are saddles or centers. So when there are centers and traps, you can prove mixing outside of the trap. When there are only simple saddles, I proved in some paper which is in Annals of Mathematics in 2012. It's actually, it was not my PhD, it was the question of my PhD thesis, but I solved it maybe 2 years after my PhD. And it was a conjecture by Arnold on absence of mixing, that if you have a minimal flow, locally Hamiltonian, sorry, dense trajectories and only saddles, you fail to be mixing. And as you say, what you really prove, you have a criterion that if your flow is sufficiently rigid, I will not define that, and you don't have shearing, then you do not have mixing. So this rigidity is some feature of this type of systems. So with some additional assumption, then you are right. Mixing is the only mechanism for, shearing is the only mechanism for mixing. And this, there's a criteria in this direction for special flows that are due to Kochergin and his work in the 70s. And this is the starting point of my work and the work of other people who have proved the absence of mixing results. And there, what you really have to do is to show that there is no shearing. So if you show that along some rigidity sets, along some subsequence of times, you fail to have shearing, then you can deduce absence of mixing. And actually, I do some sketches of this in this lecture series at the HS, but I don't think you want to look at 8 hours, of course, but maybe, I don't know, I can tell you more, I can, yeah, so. But so there are, yeah, so this is true for some, under some additional assumptions, negating shearing prohibits mixing. Does this answer your question? Yes.
Yes, thank you.
Yeah. Thanks a lot for the question. Give me a chance to say much more.
Maybe I ask you a quick question, just so something we discussed together, but maybe you can make a comment which is for the general public. I mean, we actually discussed the fact that, as you know, I like a lot the connections between dynamics and number theory, and in renormalization of elliptic systems, there are a lot of number theoretical conditions which are needed, but indeed some sort of new number theoretical conditions arise also in your work on mixing.
Yes.
Can you perhaps just say a few words about this?
Yes, I
accessible
wish
to everybody without being too technical. Okay.
Yeah, no, I wish I had. So sometimes, given that's where I have a hint of this aspect towards the end, but I removed. I have some slides, but it's hard to find them now. But so okay, so it's maybe I will just go to. Let me draw this. Let me just go to have a picture behind this renormalization picture. This picture where just one slide I had about. This is a super system where you move your dynamical system in the space of dynamical systems with the same features. And okay, so as Stefano says, and it's one of the expertise of his research. So and also people who do maybe KAM or Hamiltonian dynamical systems and twist maps or KAM. So it's very important when you study some dynamical systems to have what are called Diophantine conditions. For example, if you have a rotation on the circle, somehow, or a diffeomorphism of the circle, which has a certain rotation number, as some arithmetical aspects of how well this rotation number can be approximated by rationals play a crucial role in the dynamical description or understanding of the system. So these are called Diophantine conditions. They come from Diophantus and how well an irrational number is approximated by rationals. And Diophantine conditions also have a meaning in terms of renormalization. So in this picture of renormalization, they are related to how recurrent an orbit is. So if you have this this renormalization as a dynamical system on the space of dynamical system, if it's very well recurrent, this corresponds to having strong Diophantine or good small divisors property. Okay, so especially closed orbits for the renormalization correspond, for example, to quadratic irrationals and badly approximable rotation numbers. Okay, so a big technical part, which is indeed a lot of my contribution to this story and to these results, which I didn't touch upon, is about developing analogous type of conditions for higher genus. So when we don't have a torus, but we have a surface of higher genus, you may also want to impose Diophantine-like conditions. Actually, I'm going to be speaking at the ICM in St. Petersburg this summer, and I had already to write the proceedings for the ICM. I think Stefano has read a draft of the version, and I titled the talk Dynamics and Arithmetics of Surface Flows. And there is the focus of my proceedings and talk at ICM would be exactly on what are these Diophantine-like conditions in higher genus. And they maybe lose a bit of the arithmetic meaning, but it's essentially you can now have a system with more than one frequency. You don't have a torus, but you have a higher genus surface, so there's more than one frequency. And by the way, this I should quote Stefano. So Stefano has done seminal work together with Jean-Christophe Yocoz and Pierre Moussa. They have done seminal work in the linear case, in the case of linear flows on higher genus, in exactly defining good Diophantine-like conditions to study the dynamics of these flows. And this is really seminal and very influential work. And they proved indeed hard results, like the full measure of this condition, that they are typical. And what I do in my work, sometimes I also exploit some of the work of Marmi Moussa Yocoz and Avila Guzel Yocoz. Other people have proved that certain features of renormalization are typical. And part of my work is to interpolate between the dynamics of renormalization, which gives you good recurrence and good Diophantine conditions in this higher genus setting, and what you need to understand the dynamical system. So I often define some very specific and technical Diophantine-like conditions. Then I exploit the works of others to say that they are typical. But these conditions then play a key role when you really have to prove mixing, weak mixing, higher order mixing. So does this what you was trying to understand? So it's true, it's a very crucial part, but unfortunately I didn't want to, I think it's too technical for this audience, but thank you for giving me the opportunity of hinting at it. And so maybe I'll post it's not online yet, but I have to the proceedings of the ICM will talk, will be a survey in this direction. So maybe if anybody's interested, I can send you a copy of that preliminarily if you want. Yeah. And, thanks a lot. Yeah.
Okay, I guess if Stefano has no objection, we can conclude thanking Corinna, because it was really a very successful presentation and selection of points to stress. We go home with some extra.
I'm happy.
Thank you very much.
I'm trying to my best.
No, sorry, there is another question from Bruno Bucciotti, but then after that we will close. Bruno, please ask the question.
No, I was just clapping, not raising my hand.
Ah, clapping. Sorry, I misunderstood. Okay, no, sorry. Thank you very much then.
Thanks to everybody for listening.
Okay, it was a pleasure.
Grazie, Corinna.
Yeah.
Okay.
Thank you.
Bye.
Thanks a lot.
Ciao.
Bye.
Grazie mille.
Ciao.
Grazie ancora per l'invito.
Ciao, grazie. Ciao.